Okay, hi everyone, welcome back to this video series on data centers. Reliable Transport Protocol EIGRP uses a proprietary protocol called Reliable Transport Protocol RTP to manage the communication of messages between EIGRP speaking routers, and as the name suggests, reliability is a key concern of this protocol. Cisco has designed a mechanism that leverages multicasts and unicasts to deliver updates quickly to track the receipt of this data. When EIGRP sends multicast traffic, it uses the Class D address 224.0.0.10. Each EIGRP router is aware of who its neighbours are, and for each multicast it sends out, it maintains a list of the neighbours who have replied. If EIGRP doesn't get a reply from a neighbour, it will switch to using unicasts to resend the same data. If it still doesn't get a reply after 16 unicast attempts, the neighbour is declared dead. People often refer to this process as reliable multicast. Routers keep a track of the information they send by assigning a sequence number to each packet. With this technique, it is possible for them to detect the arrival of old, redundant or out of sequence information. Being able to do these things is highly important because EIGRP is a quiet protocol. It depends upon its ability to synchronize topology databases at startup time and then maintain the consistency of databases over time by communicating only when a change occurs. Diffusing update algorithm. EIGRP uses diffusing update algorithm DUAL for selecting and maintaining the best path to each remote network. This algorithm allows for the following: determining a backup route if one is available, support of VLSMs, dynamic route recoveries, queries for an alternate route if no feasible successor route can be found. DUAL provides EIGRP with possibility the fastest route convergence time among all protocols. The key to EIGRP's speedy convergence is twofold. First, EIGRP routers maintain a copy of all of their neighbours' routes, which they use to calculate their own cost to each remote network. So if the best path goes down, the solution may be as simple as examining the contents of the topology table to select the best replacement route. Second, if there isn't a good alternative in the local topology table, EIGRP routers very quickly ask their neighbours for help finding one. This reliance upon neighbour routers plus the behaviour of leveraging the information obtained from them accounts for the diffusing quality attributed to DUAL. The EIGRP Hello protocol enables the rapid detection of new or dead neighbour, and RTP provides a reliable mechanism for conveying and sequencing query and query response messages. DUAL then grabs the baton and is responsible for the selection of the best paths and for maintaining relevant information about them. Route discovery and maintenance. The hybrid nature of EIGRP is revealed in its approach to route discovery and maintenance. Like many state protocols, EIG supports the concept of neighbours that are discovered via a hello process and whose states are monitored. Like many distance vector protocols, EIGRP uses the route by rumour mechanism I talked about earlier. That implies that many routers never hear about a route update firsthand. Instead, they hear about it from another router that may also have heard about it from another one, and so on, giving the huge amount of information that EIGRP routers have to collect. It makes sense that they have a place to store it. EIGRP uses a series of tables to store important information about its environment. Neighbourship table. The neighbourship table, usually referred to as Neighbour table, records information about routers with whom neighbourship relationships have been formed. Topology table. The topology table stores the route advertisements received from each neighbour about every route in the internetwork. Route table. The route table stores the routes that are currently used to make routing decisions. There would be separate copies, instances of each of these tables for each protocol that is actively being supported by EIGRP, whether it's IP or IPv6. EIGRP Metrics. Another really great thing about EIGRP is that, unlike many other protocols which use a single factor to compare routes and select the best possible path, EIGRP can use a combination of four called a composite metric. These are the four factors used to build that composite: bandwidth, delay, reliability, load. Bear in mind that EIGRP only uses bandwidth and delay on the line to determine the best path to a remote network by default. And just so you know, Cisco sometimes like to call these factors path, bandwidth value, and cumulative line delay respectively. Also worth noting is that there's a fifth element to all of this called maximum transmission unit, or MTU size, even though this element is never used in EIGRP calculations. It's a required parameter in some EIGRP related commands, especially those involving redistribution. The value of the MTU element represents the smallest MTU value found along the path to the destination network. Open shortest path first basics. Open shortest path first, OSPF, is an open standard routing protocol that's been implemented by a wide variety of network vendors, including Cisco. If you have multiple routers and not all of them are species of Cisco, then you can't use EIGRP. Now you can. So your remaining CCNA data center objective options are basically RIP, RIPv2 and OSPF. If it's a large network, then really your only options are OSPF and something called route redistribution and translation service between routing protocols. And again, I personally recommend avoiding both versions of RIP whenever possible. OSPF works by using the Distrika algorithm, wherein first a shortest path tree is constructed and then the routing table is populated with the resulting best paths. OSPF converges quickly, although not quite as fast as EIGRP does. It supports multiple equal cost routes to the same destination, 8 by default, but you can configured up to 16, and like EIGRP, it supports both IP and IPv6 router protocols. OSPF supports the following structures: support areas and autonomous systems, minimizes routing, update traffic, allows scalability, supports VLSM, CIDR, has unlimited hop count. It is open standard, permitting multi-vendor deployment. OSPF is the first link state routing protocol that most people are introduced to, so it's good to see how it compares to the traditional distance vector protocols such as RIPv2 and RIPv1. Table 10.3 displays a comparison of these protocols. Characteristic: OSPF, RIPv2, RIPv1. type or protocol, link state, distance vector, classless support, yes, yes, no, VLSM support, yes, yes, no, auto summarization, no, yes, yes, manual summarization, yes, no, no, discontiguous support, yes, yes, no, route propagation, multicast on change, periodic multicast, periodic broadcast, path, metric, bandwidth, hops, hop count, non 15, convergence, fast, slow, peer authentication, yes, yes, no, hierarchical network requirement, yes, using areas, no, flat only, updates, event triggered, route table updates, route computation, Districata, Bellman Ford. OSPF has many features beyond the few I've listed in table 10.3, and all of them contribute to a fast, scalable and robust protocol that can be actively deployed in thousands of production networks. OSPF is supported to be designed in a hierarchical fashion, which basically means that you can separate the larger internetwork into smaller networks called areas. This happens to be the best design for OSPF. There are three big reasons for creating OSPF in a hierarchical design: to decrease routing overhead, to speed up convergence, to confine network reliability in single areas of the network. Of course, none of these make configuring OSPF easier, only more elaborate and difficult, but it's seriously worth the trouble. However, with all that said, it's important that you understand the drawbacks of link state routing protocols. First, understand that in addition to the routing protocol table, link state requires a topology database and a neighbor table referred to as an adjacent database. This will result in a significant amount of memory and processing in large or complex networks. It's important that your network design is solid, especially in large or complex networks. Let's take a look at the design that OSPF desires: the hierarchical network. Figure 10 shows a typical true simple OSPF design. Pay particular notice to the fact that some routers connect to the backbone area called area 0. When configuring multi-area OSPF, you must first have an area 0 and all other areas should connect to this. Make a note to yourself that any areas that do not directly connect to an area 0 can still be connected via virtual links. The routers that connect other areas to the backbone area within the AS are called area border routers, ABRS, and still at least one interface of the ABR must be in area 0. OSPF runs inside an autonomous system, but it can also connect multiple autonomous systems together. The router that connects these autonomous systems is called an autonomous system boundary router, commonly referred to as an ASBR. Ideally, you would create areas within networks to help keep route updates to a minimum in really large networks. This provides redundant frequency for shortest path first SPF calculations. Doing this also keeps problems from propagating throughout the network, isolating them to a single area within it, which makes troubleshooting a lot easier because routing tables are smaller. OSPF terminology. Imagine how challenging it would be if you were given a map and compass but had no knowledge of east or west, north or south, river or mountain, lake or desert. You'd probably not get very far putting your new tools to good use without knowing about this stuff. For this reason, you will begin your exploration of OSPF with a long list of terms that will prevent you from getting lost in the later sections. The following are important OSPF terms to familiarize yourself with before you proceed. Link. A link is a network or router interface assigned to any given network. When an interface is added to the OSPF process, it's considered by OSPF to be a link. This link or interface will have state information associated with up or down, as well as one or more IP addresses. Router ID. The router ID or ID is an IP address used to identify the router. Cisco chooses the router ID by using the highest IP address of all configured loopback interfaces. If no loopback interfaces are configured with addresses, OSPF will choose the highest IP of all active physical addresses. Neighbour. Neighbours are two or more routers that have an interface on a common network, such as two routers connected on a point-to-point serial link. Adjacency. An adjacency is a relationship between two OSPF routers that permits the direct exchange of route updates. OSPF is really picky about sharing routing information, unlike EIGRP, which directly shares route with all of its neighbours. Instead, OSPF directly shares routes only with neighbours that have also established adjacency. And not all neighbours will become adjacent. This depends upon both the type of network and the configuration of routers. Hello Protocol. The OSPF Hello Protocol provides dynamic neighbour discovery and maintains neighbour relationships. Hello Packets and Link State Advertisement LSAS build and maintain the topological database. Hello packets are addressed to multicast address 224.0.0.5. Neighbourship database. The Neighbourship database is a list of all OSPF routers for which hello packets have been seen. A variety of details, including the router ID and state, are maintained on each router in the Neighbourship database. Topological database. The topological database contains information from all of the link state advertisement packets that have been received from an area. The router uses the information from the topology database as input into the Discartra algorithm, and that computes the shortest path to every network. Link state advertisement. A link state advertisement LSA is an OSPF data packet containing link state and routing information that's shared among OSPF routers. An OSPF router will exchange LSA packets only with routers to which it has established adjacencies. Designated router. A designated router DR is elected whenever OSPF routers are connected to the same multi-access network. Cisco likes to call these broadcast networks, but really they are networks that have multiple recipients. Try not to confuse multi-access with multipoint, which can be easy to do sometimes. A prime example is an Ethernet LAN. To minimize the number of adjacencies formed, a DR is chosen, elected to disseminate receive routing information to from the remaining routers on the broadcast network or link. This ensures that their topology tables are synchronized. All routers on the shared network will establish adjacencies with the DR and backup designated router BDR. I'll define this next. The election is won by the router with the highest priority, and the highest router ID is used as a tiebreaker if the priority of more than one router turns out to be the same backup designated router. A backup designated router BDR is a hot standby for the DR on multi-access links. Remember that Cisco sometimes likes to call these broadcast networks. The BDR receives all routing updates from OSPF adjacent routers but doesn't flood LSA updates. OSPF areas. An OSPF area is a grouping of contiguous networks and routers. All routers in the same area share a common area ID. Because a router can be a member of more than one area at a time, the area ID is associated with specific interfaces on the router. This would allow some interfaces to belong to Area 1, while remaining interfaces can belong to Area 0. All of the routers within the same area have the same topology table. When configuring OSPF, you've got to remember that there must be an Area 0 and that this is typically considered the backbone area. Areas also play a role in establishing a hierarchical network organization, something that really enhances the scalability of OSPF. Broadcast multi-access networks such as Ethernet allow multiple devices to connect to or access the same network, as well as provide a broadcast ability in which a single packet is delivered to all nodes on the network. In OSPF, a DR and a BDR must be elected for each broadcast multi-access network. Non-broadcast multi-access MBMA networks are types such as frame relay, X25 and asynchronous transfer mode ATM. These networks allow for multi-access but have no broadcast ability like Ethernet, so NBMA networks require special OSPF configuration to function properly, and neighbor relationships must be defined. Point-to-point. Point-to-point refers to a type of network topology consisting of a direct connection between two routers that provides a single communication path. The point-to-point connection can be physical, as in a serial cable directly connecting two routers, or it can be logical, as in two routers that are thousands of miles apart yet connected by a circuit in a frame relay network. In either case, this type of configuration eliminates the need for DRs, BDRs, but neighbors are discovered automatically. Point-to-multipoint. Point-to-multipoint refers to a type of network topology consisting of a series of connections between a single interface on one router and multiple destination routers. All of the interfaces on all of the routers sharing the point-to-multipoint connection belong to the same network. As with point-to-point, no DRS or BDRS are needed. All of these terms play an important part in understanding the operation of OSPF. So again, make sure you're familiar with each of them. Reading through the rest of this chapter will help you place the terms within their proper context. So with all that, let's move on now and get actually configuring the routing protocols on our Nexus 7000. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.